des progrès. Salut, je fais des progrès. C'est pas encore ça, mais je fais des progrès. Et je vais tester les mots. Sur ton écho, c'est ça.
I'm using right now
Et tu sais les recharger? Tu les recharges avec un USB. Et donc tu as
All right, I think we're going to get started. Good morning. Welcome back, everyone. To kick things off today, it's a pleasure to have Ruofan Jiang from Berkeley. We're talking about Mumford, Tate, André, Oort, but modpAx.
Okay, so
but.
not modpAx. It's like those conjectures just get famous, but modpAx is actually famous. So I guess like this talk was supposed to be given by Laura. Actually cannot make it to the talk, so that's why I'm here, and I will be the entertainer. Sorry.
You are Aloha.
Aloha.
You're Laura for today.
You are Aloha for today.
Aloha for today.
Maybe not for today. You are, but right now you are Aloha.
Yeah. And I'm Laura, yes. And yeah. So and thanks, Jacob, for giving me this chance to be an entertainer with this morning. And okay. And let's just get started. So let me just get started by like the small Tate conjecture in part 0. And it's like this thing that everybody's familiar with. So for A, I always denote, use A to denote abelian variety, and K, well, at least in this page, it's a number of fields, and just like the sitting as I see. And if A is just like a abelian variety over C, and you can talk about its Betti cohomology, and well, there's a whole structure associated to this Betti cohomology, and this is like actually a representation of the Dilling torus into this this Betti cohomology tensor to R. And the Mumford group is like, well, you can define it to be the smallest Q group containing this image. And if your abelian variety is actually further defined over a number of K, and then you can talk about this Galois representation, L-adic Ital cohomology, and that's going to be a Galois representation, and that's why you get this new Galois group over K to this guy. And the L-adic monodromy group is actually can be simply defined to be the Zariski closure of this image. Okay, and the thing is like the conjecture for Mumford conjecture kind of like relates these two types of monodromy group. It's kind of relating the Betti one and the L-adic one, and it's saying what the Mumford group tensor to QL is going to be the connect component of this L-adic Galois group, L-adic monodromy group, and this guy is actually connected because it's like the smallest group containing the image, so you can always take the connect component. Okay, and so of course, like this conjecture can be said more generally for any. Not restricted to abelian varieties, but like any projective smooth number field. But let me just talk about abelian variety today. And for abelian variety, you can actually prove one direction is correct, and there's like GL circle lies in the Mumford group. And this is like by showing the Hodge plus absolute Hodge. That's like by like the linear plus eccentric. And the inverse direction is open, but even though it's open, a lot of cases are known. For example, Sarah proved that if it's a simple abelian variety, then it's going to be how to say like simple abelian variety of dimension, then this conjecture is going to be true. Okay, but the thing is like if it's even dimensional, even for simple abelian variety of simple abelian fourfolds, the conjecture is like nothing. Okay, and of course, like you can put this conjecture inside a more general context. You can compare it with Hodge and Tate conjecture. And the thing is like these three conjectures are kind of intimate friends. And if you know any two of them, and just you know the third one. Okay. And of course, like this is comparing Betti to algebraic. This is Ital to algebraic. This Betti to Ital, right? So, and there's like some applications. Of course, you can deduce case of Hodge Tate conjecture from the Mumford Tate And that's like some classical application, right? So like you know Oort conjecture, know Mumford Tate, and you can prove Tate conjecture by joining these two conjectures. And you can apply to Shimura varieties, and whenever you have like Shimura arithmetic application or kind of like something over number field, this conjecture can have like secret appears. And there's like some other application I just aware recently. There's like North called property of abelian varieties, and it's basically somehow like well it's basically something like the finiteness of isogenic class of abelian varieties of bounded Fabian-like. And they are managed, Kiss and Mox kind of like managed to reduce this conjecture to the Mumford Tate. Okay, and okay, so the main thing that we're going to talk about today is like the Mumford Tate conjecture and CARP. So this is like less familiar, and I say is well, so in this slide, in this particular page, I'm going to fix K to the CARP function field. Okay, and what happens if your abelian variety is defined as a CARP function field? And one of the biggest problems is like there's like no Betty homology, and you cannot make sense of what structure, and you cannot define this Mumford Tate. One of the possible remedies is like if you just look at those ordinary abelian varieties, and you can make sense of Mumford Tate group. Okay, so ordinary abelian variety is just like those abelian variety with maximum amount of repeat torsion points. That's like most of the definition of that. And okay, so now let's assume A is the ordinary principal polarized abelian variety. So this principal polarized can be removed by a Zarius trick, but let's do a principal polarized abelian variety. It's easy to state the things. And one can make sense of a Mumford Tate group as a generic Mumford Tate group of smallest Shimura variety, AG. Small p reduction contains the k point corresponding to A. Okay, so this definition is a little bit sketchy because I haven't told you like what means by mod p reduction, right? So those things are kind of like defined over a number field, but the things like to talk about the mod p reduction, you need to have an integral model. But for AG, I can always fix a canonical integral model, and somehow like I just replaced this k by some finite extension. Okay, and the smallest Shimura subvariety is kind of like a rational subvariety defined over some number field, but its mod p reduction is just like a mod p reduction of this Zariski closure. Okay, you may wonder, well, if you just take naive Zariski closure of something like that, some other thing, the Zariski closure is usually to be bad. But the thing is, like if you restrict it to the ordinary locus, the Zariski closure is actually going to be good. So that's something I'm going to talk about in 20 minutes when I talk about linearity.
So where to translate your definition purely characteristically?
Well, there's like some characteristic zero thing involved.
No, I see that, but the question is whether we could bypass that.
Bypass of.
And we could. Is it?
Oh, I mean, you wanted a purely characteristic P definition. That item.
Ask also, is it equivalent to say take the canonical lift and look at the smallest more vertical containing that point?
Yeah. So the canonical lift. So you need to first make sense of the canonical lift of let's say a function field value point. I guess it's actually appearing in the work of Chai, and you can do this thing. Yeah. And other question? No. Okay. And the idea behind this definition is like, well, it's just like an analogy of car zero story. Right? If K is a number field, then the Mumford Tate group is just like a generic Mumford Tate group of the smallest Shimura variety containing it. So that's why kind of like mimicking this fact here, so kind of like gives this definition. And also, why you need to restrict the ordinary strata is kind of like ordinary strata is kind of like more or less closest to car zero thing. Of course, you can somehow modify this definition for high energy strata, but I think it's like a more involved. So that's just to do ordinary strata.
But the definition, why is small?
Oh, why can one see? Yeah, so smallest is up to ISO, like up to Hackey translation.
Yes, but even so, we can have.
You mean like more P fiber are going to be bad? Yeah, so that's
reduction could meet in character.
exactly. So I got question the same thing when I gave this talk in front of Richard Taylor. And the thing is like, okay, so the multi-fiber of this thing over the ordinary locus is gonna be like have a torus structure, kind of like this or formal torus. And the thing is like the torus structure kind of like guarantees that you don't have those bad things happen.
The definition requires to be ordinary.
Ordinary, yeah. So yeah, this definition is actually very technical. So in order to make it clear, I mean that's the only thing I can do. But anyway, so for many applications or for studying it, it's sometimes very useful to talk about this geometric version. Also, instead of talking about this function field, we can spread out it a little bit, and to spread out this over a how to say a smooth varieties over smooth variety over FQ, and you can define Mumford group in the same way, just like you take this X map to the modalized space and take smallest from Shimura variety containing. Okay, so there's an analogy of the Mumford conjecture for the ordinary Shimura variety, which at least appears in, I mean, a baby form of this appears in Chai's unpublished work, and it says, well, if A is a abelian scheme over a geometric smooth, let's say variety over FQ, and this of course gives you a map into the modalized space, and I require this to be like generic ordinary image. Then you have this Mumford tensor to QL is QL. I mean this LL monodromy group to the connect component. So the LL monodromy group now is kind of like where you have this this étal fundamental group mapping to each one of the étal cohomology, and you take the image and take a Zariski closure. Okay. And when L equal to P, of course, like there's no, a p-adic étal cohomology is like not a good cohomology there. So you need to take the the monodromy of something called overconversion of isocrystals, which are kind of like p-adic analog of DC sheets. Okay. So of course, like there's some bunch of applications of this, or you can use it to somehow deduce conjectures, Tate conjecture in car P. I mean, join with Oort conjecture in car 0. And maybe you can still talk about this North called property. You can do this again. And there's something called S-integrality conjecture, which is like highly related to the thing that the Picard jumping problem Anand is going to talk about this afternoon. And this actually, if you use Mumford conjecture, you can get much stronger results. So that's an ongoing work. And the thing I really want to talk about today is like the application to multi unlikely intersections. And as I wrote in the abstract, that those three conjectures, modpAx Lindemann, André Oort, and this Mumford are kind of like very closely related to each other. Okay, so one thing that I can prove is the conjecture is true if F factors through a product of G-spin Shimura varieties. So G-spin here is basically orthogonal Shimura variety. And let me give some examples, right? So U1 and Shimura variety are unitary Shimura variety that containing G-spin Shimura variety. So this actually appears a lot in those CUDA program. And the modalized space of K3 surface are kind of like G-spin 219, and modalized space of abelian surface is actually G-spin 2-3. Okay. Okay. So next one, yeah. So I've talked about it. Like I want to do this multi-unlikely intersection. So let me quickly mention this background on André Oort conjecture in car 0. So so the statement of the conjecture is like this. If S is a Shimura variety and there's a subvariety Y contains a Zariski dense collection of CM points, then Y is going to be special. Okay. So this conjecture is like considered solved. And I mean, since it's, this conjecture is like raised in 1990s, and in the past 30 years, a lot of people have worked on that. So I'm sorry, I haven't typed out all of the list of numbers, but I believe half of our audience is like work, maybe directly or indirectly work in this conjecture. And yeah, so because everybody's like very familiar with this conjecture, so let me just stop introducing like those all minimal stuff. Let me just go into car P directly. So you can try to formulate this conjecture in car P, and people did actually. So one of the problems like the naive formulation is actually wrong. So what is naive formulation? Well, if you take a Shimura variety, FP tensor to FP bar. So F here I always mean FP bar, and you take a sub-variety, and you can claim what is special, or you can conjecture it's special if it contains a RC dense collection of CM FP bar points. But this is actually wrong. The reason why it's wrong is like every FP bar point is CM. So it seems like if this conjecture is right, then every sub-variety is going to be special. So of course, like you cannot expect this.
Can you explain the
Oh, I mean that's some, I guess like some theorem by Tate or maybe Sarah, one of them. It's just like over FP.
One person, okay.
Over FP bar, it's just like a billion variety has like this Frobenius, and you have like a much larger endomorphism for it. And by special, I mean it's a component of modular reduction of a special variety. So there are several remedies. So people do have like consider like modp analogs. So one of the analogs is like arithmetic version is given by Alex Solfen and Richard. So like, well, the key point is like replacing CM FP bar point by some other collection, which is like a little bit stronger. So the collection they give is like a reduction of CM points out of number field. Okay, so that means, well, this one is kind of like finite extension. So here, somewhat it means like X as a FP bar variety, a CM point on this X is no longer the FP bar point, but kind of like a cluster of points. Okay, so now it's actually stronger, right? You can imagine like, if a CM point is like a cluster point, it's going to be much stronger here. And they prove this like for modular curves and product modular curves, condition on GRH. And of course, you can also try to formulate a geometric version, which you replace the CM FP bar points by special function value points. And of course, you can to make sense of what special means. But here you can make it into. I mean, it's more convenient to just say, well, it contains Sarski dense collection of positive dimensional special subvariety. Okay, and the thing is like you can say, well, if X, you can conjecture that if X is special, if it contains a Sarski dense collection of positive dimensional special subvariety. But unfortunately, this does not guarantee that X is special. So here is a counterexample. So it's a triple product modular curves. Instead of reading this, I'm going to draw something on the board. It's just much easier to understand. So the thing is like, let's say X, and it's kind of like it's a cube. And what I can do is like, I can pick a non-special curve, just like a random one, and it's just product with a third copy. And I get a trivial Lewis surface. And this is my subvariety, let me call it Y. And the thing is, because every FP bar point on C is going to be special, and its product with this third copy of modular curve is going to be special. So it admits a special collection of special subvariety, but the whole thing is not special. So that's a counterexample. And the conjecture is actually, this counterexample is the only obstruction. Okay. So let me call it like actually geometric version of what the André Oort conjecture. So actually, the André Oort conjecture I'm talking about today is this geometric version. Okay. And well, so blah 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 is an ordinary subvariety contains a Sarski dense collection of positive dimensional multi-special subvarieties, and then claim X admits a positive dimensional special factor. So you cannot say X is special, but you can say X is special factor. For example, in this example, it has a non-special factor, which is a curve C, but it has a special factor, which is the third copy of modular curve. Okay.
So is that a notion of weakly special?
Yeah, so this is like maybe like a weakly special. So it's weaker than a weakly special. That's kind of quasi-weakly special. Okay.
No, go.
By factor, you mean it's an actual product or a factor?
Naively, it's almost a product, but the thing is like, in the context of Shimura varieties, kind of like there is a product of Shimura data sitting inside it, and one copy of Shimura data gives you the vector, another copy of Shimura that contributes some non-special vector. Okay. So what I can prove is like the conjecture is true for product of G-spin Shimura varieties, and if this guy is already, I mean, if it's a single G-spin Shimura variety, then X is already special. This is actually by some group theory reason. Okay. So in the rest of the time, I'm going to go deeper into the characteristic keywords, and I'm going to talk about like some deeper structures for Shimura varieties in characteristic P. Okay, so that's basically the schedule, and I'm going to talk about this modpAx Lindemann, which appears in the abstract, but I haven't introduced it yet. So we start by this formal linearity. So by linearity, well, first let me motivate it. So what is linearity? So in car zero, I guess everybody's like familiar with this. There's like Shimura varieties are, well, portions of hyperbolic space, and special varieties are kind of like, well, linear in the hyperbolic coordinates. Linear, by linear I mean it's totally geodesic. And the converse is also true if the linear subvariety contains a CM point. So that's actually a very beautiful characterization of special subvarieties in character zero. And the thing is like, the natural idea is like to generalize this to car P, but the thing is like, a naive formulation or kind of like a naive generalization is kind of wrong, because like, for example, there's no good uniformization theory and there's no hyperbolic geometry, for example. Okay, and one of the candidates that you can do is like, well, you look at formal linearity. So that's a little bit easier in car P. So its name suggests the formal linearity has something to do with the formal completion. So here, this definition is like stems from something called Tate moduli or Tate formal torus. So it says, well, if X, okay, let's take this Shimura variety AG and the sigma moduli space, and you take X in its mod P fiber, okay, and let's require it to be ordinary. Then this guy. Okay, W is the width vector of F. Okay, if we complete that X, it's canonically a formal torus. Okay, so this is called Tate torus. Okay. Okay, so now the torus structure is actually giving the formal linearity, and we're going to call this formal linearity. And definition is like a subscheme, mod P subscheme inside AG. A special fiber is called Tate linear at X if its completion at this point, at the ordinary point, it's a formal subtorus of the Tate formal torus. Okay. And what Chai can prove is actually if a scheme is like Tate linear at one point X, is going to be Tate linear at every point, at least at every smooth point, using a theory of globalized Tate formal torus. So you can, yeah.
Maybe a silly question. What does the /x in your notation mean?
Oh, it's completion. Okay, so that's Chai's notation. And right, so there's actually a global version of Tate formal torus. You can just do it kind of like in family, and we're going to come back to this point later. Okay, and you can use this formal linearity to formulate this linearity, like to mimic the linearity in car zero. You can say, well, does this formal linearity characterize special subvarieties? And here you have this Newt theorem. I mean, the theory proven by Newt in '96, which kind of like answers half of the question. So if you have a Shimura variety, and you do the mod P, then the mod P Shimura variety is going to be Tate linear. Okay. And he did this by studying those like the formal deformation space of Tate tensors. And of course, this is just like half of the story. It does not characterize mod P Shimura variety yet, right? So mod P Shimura variety.
Only if they are linear. It's useful only if there are any.
Yeah. Only if there's like ordinary vectors. Yes. But like there's generalization to higher level strata, like you take central leaf and yeah, but it's more complicated. Okay. Yeah, so this half of the story is not a characterization yet because like you don't know the opposite direction, right? So opposite direction is actually this conjecture. If a subvariety is Tate linear, can you say what it's special? But unfortunately, this is open, and I just explained this, and this, so there's like an interesting viewpoint on this in terms of bialgebraic geometry. So the thing is like what you can do is you can think of this formal completion at a point as uniformization, but it's like somewhat like a pointwise is not strong. But now this Tate formal torus structure gives you one type of algebraic structure on the uniformization, and Y itself as a Shimura subvariety is going to be another algebraic structure. And the thing is like you have two algebraic structure, and if you have subvariety which is algebraic in the two algebraic structure, then it's bialgebraic. And somehow you should expect this Y to be special. Okay. And this actually motivates the following generalization of this Tate linear conjecture. Is calling it modpAx Lindemann, but it's actually not an exact analog. So the statement is like this: well, if you take a subvariety inside ordinary locus of your Shimura variety, then and you take a completion at a point X, and you take the smallest formal torus content in it. So this is like some formal thing. Okay, now we expect is like this guy is going to be algebraizable. So that means like there is a subvariety of your special fiber Shimura variety, so whose completion is going to be this torus. Okay, the second thing is you can claim something even stronger. This variety is actually special. And the thing is like this recovers the Tate linear conjecture. If you just take this Y to be Tate linear,
So
then
I apologize for the question.
yeah,
There would be only one Z if it was.
exactly.
Really?
Because how to say, if you have like two algebraic subvariety which is the same, if you complete at P, then these two algebraic varieties are the same. That's like some commutative algebra.
A Y appears in the statement. Can't I just take a point in a formal subtorus of the?
Yeah.
Oh, I see. So Y is sort of not.
But it's not. So,
Look, it seems to me like I could just take a point and then take a formal torus at that point.
right, and that's special, right?
Yeah, but how is Y? I just don't like.
Well,
Why
it's the smallest one.
Yes, it's the the origin of your Tate form.
Right, it's contained.
Oh, I see. Oh, it's the fact that it is the small thing containing
Yeah.
subgroup. I see.
And any other question? Good. So by the way, for Anna's question, I guess like it's somewhat like forms from the flatness of
I'm sorry.
forms from the flatness of p-adic, like the completion.
Yeah.
Okay.
The reason to conjecture it is that the locus where something remains an algebraic circle.
Algebraic. Sorry.
The reason to hope that this is algebraizable is that it's the locus where some circles remain.
Some
Cycles.
algebraic cycle,
Yes.
cut out by some algebraic cycle. Yes. Yeah. So one way to prove this is kind of like, well, you prove using this formal thing. So there's like a formal cycles here. Somehow like, so you can upgrade it to actually p-adic cycle. And then, so it's actually p-adic formal cycle. You can upgrade to actually p-adic cycle and use Tate conjecture to actually upgrade to algebraic cycle. So that's like one way to prove this. So actually this is a consequence of Tate conjecture as I realized it just maybe this year. And okay, so this theorem is true if again it's the product of reduced Shimura varieties. Okay, so let me just make a very, very quick sketch of this thing for product of reduced. Okay, so the philosophy here is there are two linearity. So the linearity of your Tate torus. There's another thing called linearity of your of the unipotent radical, not unipotent radical, I mean unipotent corresponding to the whole the Newton co-character of your monodromy, p-adic monodromy group. So this A here, okay, so let me explain what this A is. Actually, so you have Y here, which is an ordinary subvariety, and you get a abelian scheme over Y by pulling back the universal family. So I'm going to call it A. Okay, so you can talk about the monodromy group of F isocrystal. So this is GP, and you can. This is actually a reductive group, and there's a co-character which is Newton co-character mapping to this thing, and you take the unipotent of corresponding to this co-character. Take the what? Unipotent. So you have like the parabolic, and inside you have like this unipotent. Sorry. Okay. So this actually is also linear. There's a unipotent. The thing is like the philosophy is like you can these two seemingly different linearity after some like sophisticated identification they are the same thing. So here on the left hand side it's some geometric thing. On the right hand side it's like some monodromy group or like group theoretic group, and they actually give you the same linearity. Okay, so the way to achieve this is like from the following thing. Okay, so here you have something called overconvergent isocrystals over variety Y, and you can embed it into a larger category called convergent isocrystal, but not forgetting the overconvergent structure. And you can also map to this F isocrystal like restricted to this formal okay? And then it's kind of like, well, you take your first relative crystalline cohomology of A, Y, it gives you an overconvergent isocrystal, and you can forget its structure and you can complete it up from, okay? You get three objects. Okay, so the thing is like, if you look at the monodromy groups, this first relative crystalline cohomology gives you an overconvergent monodromy group GP, and this guy is like the parabolic of this GP with respect to this Newton co-character. And this is like, basically the monodromy group is the unipotent corresponding to this co-character. Okay, so this thing is actually very non-trivial. The first embedding, I mean the monodromy group of the isocrystal is the parabolic subgroup with respect to the Newton filtration is actually Crew's parabolicity conjecture, which is just proved by Diadasu in 20s. And the second arrow is Chai's local monodromy theorem. Okay, so after this, you can actually somewhat identify the co-character lattice of your formal torus as the unipotent of your monodromy group. And this actually gives you some group theoretical information, and you can use it to understand the structure of this how to say p-adic monodromy group. Okay, so once you
is always abelian.
What is always happening?
Unipotent is always abelian.
I mean it's
Because you have a abelian group on the left side.
That's right. Yes, because like it's if there's ordinary, it's always abelian. If there's like non-ordinary, it's like no.
What is special about spin femoral?
Oh yeah, I'm just going to talk about here these endomorphism. Okay, so construct endomorphism of a like once you know this monodromy group, you can use it to construct endomorphism of this P divisible group over Y, and you can actually construct a lot and use crystalline isogeny theorem to show that well endomorphism of A is big. Okay, so here one need to specifically use the group. How to say group theory of G-spin groups.
It's one idea that there are few subfemoral variety in a spin femoral.
Yeah, it's just like it's only G-spin ones and unitary ones. So it's just, I mean, the Shimura varieties are easy. So that's somehow, well, this group theory is going to work. In general, group theory is actually, yeah, it's not strong enough to tell. Yeah, and then it's like endomorphism A is big, and you can lift endomorphism A to construct a special subvariety. So here's a canonical lift. We just like pick a point and let's lift up.
So when you say G spin, you mean signature to N.
Yeah. And now you use deformation theory to show that this subvariety is what you want. Like, yeah.
So I'm understanding this correctly. You have some group theoretic information here, just sort of abstract monodromy groups, and you've proved something about them, or you're using these results about them.
Yeah.
And now to go from the sort of co-character lattice statement
Mhm.
to endomorphisms of AP infinity,
Mhm.
is that some kind of rationality claim about the
No.
monodromy group?
So rationality mean like a rationality over Q.
Yeah, something like that.
It's just over QP. And you do this rationality claim by this crystalline isolate. Everything is like over QP, but it's important that everything is endomorphism. Otherwise, you don't have Tate conjecture.
Well, that's what my question is. I'm being very vague because I don't understand exactly. But you're working in this category of isocrystals.
Yeah.
You have this very sort of sheaf theoretic data.
Mhm.
At which point, like to upgrade to a p-divisible group endomorphism seems
Yeah.
like a big step.
I mean,
I wonder
the thing is like the group theory here is easy.
Is what?
It's easy. It's like it's here. That's the point I used the G spin, or maybe orthogonal group like SO2.
So can you say something about how you use?
Oh yeah.
Because so far there's not. I just don't
Yeah,
see
so-
where the Shimura variety is relevant. So
Yeah, so let's say G spin is like because like it's unipotent or parallel. Just let's talk about SO.
You have just one copy of SO2N or could be product of copies?
I mean, original G spin is just one copy, but its subvariety can be a lot of copies of SO2N. So yeah. So
It could be over a totally real field or something.
yeah, so exactly. So the things like general Shimura variety, like of orthogonal type inside your Shimura variety is F. F is kind of like what is that? Totally real field. And you have SO, or maybe G spin, SO, some quadratic form on this field, and a restricted to Q. And like those orthogonal type Shimura subvariety of G spin is like always going to be this. If this unitary type is something like F to Q, then you restrict the unit. And that's it. And for this one, if F is like a non-trivial extension, then you have a lot of copy. And for
For step C, can have thing that if you go to the real, you can have both ignats of 2N or
I mean you exchange the
compact groups also.
compact groups. Yeah, exactly. So there's like only one real place which is non-compact. Other places are all compact.
Oh.
I mean, for G spin, I mean that's just easy group theory. Okay. And for Jacob's question, the thing is your monodromy group is like something like this. You have the Hodge cocharacter or Newton cocharacter. I mean, in ordinary cases they're the same. So it's kind of like -1, 0, 1 if you pass to the joint. And the thing is like the unipotent looks like this very thin piece, like n times 1. And actually this is very very computable actually.
also all you're using is that everything sits inside the G-spin group.
Yeah.
Because you never bring in Shimura varieties besides that. You're using that to go from this group theory
Yes.
stuff to endomorphisms is the point.
Exactly.
I see. Okay.
And the thing is, I mean, so that's somehow like group theory is easy. So yeah, so I will talk about some results like beyond this case. That's kind of like more recent result. Okay, any other question? Nope. Okay, so let's move on. I'm gonna check it. Yeah, still got 20 minutes. So let me talk about Mumford Tate. So let me remind you of the conjecture. It's so the setting is like if X is like geometric connected smooth variety over Q, and if it's image lies in an ordinary locus, then you have this Mumford Tate tensor to QL is equal to the neutral component of this arithmetic monodromy. And if I equal to P, then this like you replace this by Fi isocrystals, right? And we used this in the last slide, right? So if I equal to P, we used this here. And actually when L equal to P, you have like some more structures, or maybe it's easier to understand this structure because you have this F isocrystal, which is kind of like you have larger category you can embed into. You can somehow understand the monodromy group under those steps. It's somewhat easier. But if for some prime inorganic P you don't have this, so somehow if you want to study this thing from Ital side, it's like a little bit hard. So the proof is like really sketchy, so I'm not going to go deep in the proof. So the thing is like the modpAx generally implies this GP and Mumford Tate admits a common factor. So here I'm using the factor. Like there's one factor that's in common. Okay, now you use this companion philosophy. This is like a GL, the L-adic coefficient objects, and the p-adic ones are kind of like companion to each other, and they actually have the same monodromy group. So by same, I mean there's like some large number field and a reductive group in the number field with this representation whose base change each places gives you those things. Okay, now once you have those L-adic and p-adic monodromy group and you know they are the same, and you know these two groups have a common factor, and you can do those kind of like Galois with the tricks and use triple tariff to conclude. So this part is actually pretty technical, so I don't expect to, how to say, to fill the proof in this one slide. Okay, if you're happy with this, let me just go over. Okay. Okay, so next page, as a hindsight, we can recently do, I mean this year, is the modpAx Lindemann is equivalent to morpheme Mumford Tate. Okay, so the previous ideas or parabolicity, local monodromy, and the companion game, and you have like one more input, which is called something called Mumford Tate pairs, which is first introduced by Sayre to prove Mumford Tate conjecture in cos zero.
Sorry, this is which generality?
Yeah, which one?
This is for all Shimura. This is
For all Shimura.
Right, okay.
So you have these two, not all abelian type, let's say.
and also ordinary.
Ordinary. So Mumford Tate pairs is kind of like something like a new input, but because of time, I'm not going to explain this. But the thing is like Mumford Tate pairs is kind of like a group theoretical result is like really strong. And you can combine it with the parabolicity conjecture, which actually you can make the step that those cos zero theory cannot achieve. I mean, because like you only have parabolicity conjecture in copy. Yeah. So the thing is like if you look at this theorem, the left hand side is like somewhat like algebraization or likely intersection flavor. The right hand side is a monodromy. And there's a bridge between them. And of course, a natural idea is just like, well, can I study modpAx Mumford Tate conjecture using unlikely intersection? Like modpAx unlikely intersection. And so there's a recent result on this direction. The modpAx Mumford Tate conjecture is true for ordinary abelian fourfolds over char P a global field with every good reduction and unramified crystalline monodromy group. And of course, because there's Tate conjecture, which is claimed by Markman recently. I mean, the Hodge conjecture of abelian fourfolds is claimed by Markman recently, and you can combine the Hodge conjecture and you can take conjecture for the abelian fragments. And
So one question.
Yeah.
This isn't known in for the number field case, right?
I don't think Mumford Tate conjecture is known.
Okay. That's what I meant. Okay.
Yeah. So anyway, somebody published a paper saying like it's he proved it, but it's in the net, never published. But I asked her in chain and she says no, it's not proved. Some like last name Zhao.
Yeah.
Oh. Okay. Okay. So here, unramified means like it contains a hyperspecial subgroup. And if you're familiar with integral model of Shimura varieties, and you see, well, this actually is some of the integral condition will give you smoothness of the integral model. So I'm just really going to give a very sketchy idea about this. So first, like you can reduce to Tate linear conjecture for curves. The Tate linear conjecture is like special case of axiom. Okay, and somehow like you can build something called crystalline local Hodge loci of the rigid tubular neighborhood of this Y. Okay, so here somehow like there's this kind of all business of Berkeley August about rigid cohomology. And the thing is like, well, if you have an isocrystal over Y, you can somehow make it into a probabilistic bundle with connection over this tubular neighborhood. Then you can do is that you can use this Durham, kind of like Durham-like bundle, and you pull up all of the crystalline tensors to cut out the Hodge loci. The construction is like very similar to actual Hodge loci in cut zero. That's using crystalline cohomology. And this is a rigid subvariety of your tubular neighborhood, and somehow you can use integral periodic Hodge theory to study its geometry, and it will say, well, this is smooth formal model, and you can conclude by formal Gaga that this is like algebraic. And once it's algebraic, you can show that it contains Sarsky dense CM point, and you use André Oort. Okay, so this is like some side thing. So in the final maybe 10 minutes.
Can I ask a question?
Yeah.
So very vague.
Yeah.
But is there any hope of using your strategy to try to prove Mumford Tate for the info folds in Cat 0? And if not, what goes wrong?
Oh, Cat 0. I thought about this. One of the big obstruction. I should not go back. This probabilistic conjecture is not true, and local monodromy theorem is not true. So I don't know. So I guess like you don't know how to use like the formal structures in Cat 0. I guess like there are
What's the point as opposed to geometry?
So how to say? Actually, there's a math overflow question exactly on this. It's kind of you cannot recover the global structure from the formal structure, but in Cat you can. But yeah,
There is no formal structure actually in Cat 0, right?
You can complete that. You can complete that ordinary reduction. Yeah.
I just wanted to ask, you say characteristic 0 and or to conclude, where do your CM points come from, or they cannot?
Yeah, that's another business, but yeah, how to explain? Let me think.
Give
me 1 second. Okay, so the thing is like in Chai's work, he constructs something called Tate linear canonical lift. Why is a Tate linear variety? You can actually lift it to the formal scheme, and the thing is like this locus actually contains this the rigid point of this formal scheme, and this okay. So let me give you a name. Let's say Y is a formal scheme, and this formal scheme is kind of like how to say it's linear. It's like how to say globally linear. So like if you have a CM point, particularly every CM point lift. Every canonical lift of the CM point lies in this form. Yeah, okay. And also like quasi-canonical also lies in this form. And a question?
But do you have a way of using the geometric André Oort in this setting rather than just the true André Oort with CM points?
For CM points. True André Oort. Yeah, so
can you use geometric André Oort?
For proving this? Can I? No, because it's about CM points. And of course, one thing, you don't actually need to use André Oort. I'm just like writing the sentence here for simplicity. So Moonen in his thesis, maybe after his thesis, proved that I mean, if you have a Shimura array is like formally linear, then it's gonna be linear. I mean, formal linear in the mixed character sense, then it's gonna be linear. And that's exactly the theorem. But his theorem is like superseded by the André Oort conjecture. You can just use one André Oort conjecture. If you know this conjecture, this theorem is just one sentence. But yeah. Any other question?
Where are you using the fact that it's a fourfold here?
As what?
Where the fact that it's a fourfold. Like what goes wrong if you replace 4 with another number?
I mean, you can prove like linear conjecture for curve for any Shimura variety. Fourfold is just like you have this application to take conjecture.
Okay.
Any other question?
Just understand info folds, formal folds, modern Mumford Tate conjecture reduces to the case of Shimura, reduces to the case of curves, right?
Yeah. So the only case that's unknown is some called Mumford type, which is like it's periodic monodromy is like A1 cross A1 product itself 3 times, and that one's reduces to curve. Let me check that. Yes, 10 minutes. Let me quickly talk about the André Oort conjecture. Okay, the geometric André Oort conjecture. Okay. So the thing is like I realized later, the Tate linear plus more P Mumford Tate actually implies more P geometric integral. Okay. So you do believe this is true. So here, more P Mumford Tate by this slide implies Tate linear. So actually you can erase this. So more P Mumford Tate implies more P integral. And this one is actually a consequence of Tate conjecture. So actually, if you believe in Tate conjecture, everything is just clear. Okay, so those were first approved in 2024 for products of G-spin varieties. Okay, so now let me just begin with a baby example of how this whole proof works. So suppose AX is a surface inside the moduli space of abelian surface, which is a G-spin variety. Okay. And let me just draw something. I can reuse this actually. So this A2 is going to be a threefold. Every threefold in my word is a cube. Okay. And the thing is like, well, if you have a surface, it contains Zariski dense collection of positive dimensional special self-variety all passing through no fixed point and claim X is special. So that's the picture is briefly like this. Everything passes through one point. It's like super special case. Okay, now the proof is like this. You take all of this, those special self-varieties, let's say one dimensional, and you take the completion at that point. It gives you a formal tor. Okay, you just take the smallest formal subscheme containing all of those formal tor, right? And you get some formal scheme. And you can prove that it actually equals to X completed at this point. Okay, you just take the completion of all of those things because it's Zariski dense and of the dimensional reason, well, the union of those things, if you take this closure, is going to be X completed at this point. And it's sitting inside this larger ambient Tate formal torus. Okay, so now there's a theorem, very nice theorem by Chai. It says, well, since each of this guy is like formal torus, and formal torus is like stable under scaling. Okay, now it means like the closure is stable under scaling. That means that this is stable under scaling. And Chai told you, well, if a formal subscheme of your formal torus is stable on the scaling, then itself is going to be a torus. That's called the rigidity theorem of formal torus. And things like it implies this is a formal torus. Okay, now X is Tate linear. And you conclude by Tate linear conjecture that X is special. Okay. And the thing is like, it's a baby example. I actually haven't used Mumford Tate, right? It's just literally baby. And now I'm going to do this adult one. Okay, so for the general case, what I can do is like, you may no longer have like those special varieties like passing through one point, but the thing is, you still have, well, let's still draw a picture. It's nice to have a picture. Like this, you have a sub-variety, and you have like a bunch of special varieties just like randomly distributed. And think about the hot project. So the thing is like, well, you can make the things in families. So you do this global Tate coordinate thing by Chai. So what they do is like, well, you take X and you bed into the ambient Shimura, right? And you take the computation at the graph, and it's actually going to be a family of formal tori over your X. So it's like, well, it's like if you draw it, it's like X, and you have like a final fiber, formal tori fiber over X. It's a family formal tori over X, and it's actually a Italo system because you can take the dual and you can Italo thing, and you can do the similar thing, right? You just take the closure of all of those things and sitting inside X cross X, complete this this identity section, identity map, and the lies inside the whole thing. Okay. Now there's a global version of the rigidity theorem that you need to prove. Okay, and it says, well, because the left-hand side is stable under the scaling, then left-hand side admits a family of formal tori as a component. Okay, and then here this F is like a p-adic Lisi sheaf. And you tensor to, I mean, this Lisi sheaf actually induces canonically a formal tori on your X. And this is actually going to be a component of this formal scheme. Okay. Now this component sitting inside X plus X sitting inside this guy. And what's special about this p-adic Lisi sheaf? What you can prove is, well, it's Tanaka category sitting inside the Tanaka category generated by the Delaunay crystal of this p-divisible group. And this Tanaka category by this Tanaka formalism is kind of like the representation category of this parabolic of your GP. Okay, and you can, but Mumford Tate is known. So use Mumford Tate, you know the structure of this guy, and you know the representation category, and you go back and you know this guy, and you can use the Mumford Tate to show that F has very big rank. And the final concluding thing is, well, in the single G-spin case, the big rank thing actually implies that the rank of F is the same as the rank of the Tate formal tori of your Shimura variety. Okay, and by a squeeze argument, you're done because the left-hand side you have formal tori, and right-hand side you have formal tori. They are of the same rank. And this thing is squeezed in the middle. This one in the middle is going to be formal tori. And it implies what this guy is formal torus at the point. It's like it's Tate linear, and you conclude by Tate linear conjecture. So that's, yeah.
Can I ask a question on the line before? So you said, yeah, this one.
Yeah.
You said on the right-hand side, you know what it looks like, and how do you conclude that the smaller Tanakan category has a big rank?
So the question is twofold, like why I know this implies into here, and why do I know?
Not only you say use MT to show that F has.
Oh, it has big rank, yeah. So in the single G-spin case, you know the representation is like is irreducible. So the F is like sub-representation of the irreducible representation. If it is not zero, it's going to be the whole thing. So that's why it's kind of big.
Okay, thank you very much.
Yeah. So for product G-spin, you don't actually. So that's why you have like this special factor business. Any other question? So actually, it's already done, but I can take question.
Yeah, any questions?
Yeah, suppose you have not an ordinary point, but a mu ordinary point where the unipotent radical of the parabolic is up for the Newton.
So there's like this.
Is a B, does the same argument work?
Yeah, that's a good question. So like the group theory is kind of like harder, right? So I guess so actually it's mu ordinary is not necessarily abelian. So it's still kind of like.
But I suppose in some cases.
I suppose it's abelian.
It will be abelian actually because there's a Newton-Hodge.
When it's mu ordinary, it's always.
So the Hodge is going to be the Galois average of Newton. The other way, Newton is going to be the Galois average of Hodge. So because it co-categories inside G, not G and C, it will be abelian.
Okay.
Okay, so and one thing I want to say is like even it's abelian, the group theory may be different.
It wouldn't be a formal torus.
It would be formal torus in like some more generalized like coordinate. Like so, actually, Moonen has proved like in mu ordinary case there's something called cascade, and it's well maybe, I mean it's actually conjectured to be a formal something called sub cascade. Maybe it's not a conjecture. Actually, it's proven by somebody like Chai or something. Yeah. Yeah.
Can I just ask this? So in the G-spin case,
yeah.
you use this representation theory to show you have endomorphisms and such. Put it that way. I'm trying to understand. In the general case, you have this work that says in general, if you have Mumford Tate, you can still conclude.
Oh, general case is like you only know these two things are equivalent, but you don't know if this is conjecture.
Yeah. But let's say I give you Mumford Tate. I'm trying to understand how the right-hand side implies the left-hand side.
Right-hand side implies left-hand side because the Mumford group, if you know the Mumford conjecture, the tensor to QP is going to be GP, right? So that's crystalline monodromy group. And by parabolicity conjecture, it's actually going to be, let's say, this is, let me call it D F isocrystal. And the D, you forget D, and this is like a parabolic. That's parabolicity conjecture. And by Chai's monodromy conjecture, monodromy theorem, if you kind of like, how to say, do this crystal over a periodic, over the formal completion, and this is given by the unipotent. And this unipotent is actually gonna be this formal torus. How to say yeah, the thing is like, if the Mumford conjecture is true, then you have all of those things, and this guy will be the expected dimension. Like this guy defines a Shimura variety, and after all of those transform, this Shimura variety, I mean, your unipotent is separated. So like the dimension are the same, and you squeeze the dimension, and yeah, that's it. Thank you. Any other question?
I actually had a question. There's this theorem of, I think, Brandner and Tellman, where they show for like a mod P Calabi-Yau, the deformation functor is like a formal torus as well.
Yeah.
So like, what could you, I mean, obviously we don't know some stuff in that context, but what could you hope to like prove there?
In the model space at Calabi-Yau.
Yeah.
It's going, yeah, I don't know for now, but like again, think a little bit. Sure. Yeah.
Do you have a mod p Channel theorem, or and what would be equivalent to it?
That's also a good question. Yeah, maybe, but I cannot formulate it right now. I used to call this mod px channel. I mean, mod px Lindemann, mod px channel. And Jacob told me like this should be called x Lindemann. So.
No, because X channel should be, you take a formal torus,
yeah,
you intersect it with a subvariety, with the formal completion of a subvariety, you get some locus. Then you ask, what is the smallest sort of guy containing that? Is that a special variety? And because it's always your algebraic structure. In your world, one algebraic structure is the one downstairs, and just varieties in AG. The other one is just tori, right? Or you can look at other subvarieties of formal torus, but you could look at tori.
Yeah.
X Lindemann is about containments, what you're proving here. X channel will be about this intersection.
Right. So, okay, yeah.
One point is the formal tori the formal tori don't have canonical algebraic, doesn't have canonical algebraic structure.
Right. Which is why subtori are better to look at.
Okay, any other questions? All right, let's thank Ruofan Jiang. You can be